Yeah, sorry for the technical difficulty there. The question was the answer key. I have mixed feelings about the answer key. On the one hand, you can always look it up, and looking it up will be one way to check your answer. And since you have the internet and book resources available, it's actually good because you could learn more about the particular problem. On the other hand, I can understand why you want the answer key, but once you start working in science in general, there is no answer key because if somebody's already done the work, then why repeat it? Unless that's the purpose of the experiment. Oftentimes we'll repeat it, and there is some potential answer there, but you're not always looking at getting the same answer. You want to get an independent answer of what their answer is. And so this goes back to the NASA astrobiologists. When they repeated those experiments, they weren't looking to get the exact same number of arsenic content in the bacteria that they got. They just wanted to confirm it on their own. So in another sense, not giving the answer keys is how you're going to be doing most of it. And so to have the answer key, it's always nice to have, but most of the time you don't have it when you're actually working in science. But I can post the answer key. I'll eventually post it. We're going to look at that, I think, in the second or the last third of class today. We'll take a look at that. Chapter 10 deals with quantity relationships. So what I'm going to do, since the projector is not working, I don't know what happened to it. It's not connecting. I'm just going to do the lecture on the board. This is a topic that's quantity relations is just stoichiometry. Stoichiometry is equal to quantity relationships. And so we're going to have different ones. The easiest way of representing the quantity relationship is by mole or molecule or formula units. So by far the easiest is by mole, molecule, formula unit. Either one of those. So for example, if I look at this, I could treat this as one molecule. What's the name of this one? Methane. Yeah. I can treat it as one molecule of methane, a dozen molecules of methane, or a mole of methane molecules. A mole of methane molecules would be an Avogadro's number's worth of methane molecules. And methane is the primary component. Natural gas is actually a mixture, and it depends on where you live. It's just slightly different. So for example, the natural gas in Hawaii is different than the natural gas in California, which is different than the natural gas on the East Coast. And so methane, however, this would be, typically we just do it, because we don't do it usually by molecule. The problem with doing it by molecule is that there are two isotopes of carbon, carbon-12 and carbon-13. So if we do it by molecule, is this methane with a carbon-12 or is this methane with a carbon-13? And then there are two isotopes for hydrogen, actually three if you count tritium. But if we're doing it by molecule, then we have a lot of different molecules. How many different molecules do we have to choose from if we do it by single molecule? If we do it by molecule, let's figure out how many different molecules there are. Is that mine? Let's see. So we have C12, and then we have 4 hydrogens attached to it. And the most common hydrogen will be hydrogen 1 or hydrogen 2. Hydrogen 1. So we have a methane molecule that's going to weigh about how much, just roughly? About how much 16. This is. Yeah, this is going to be about 16. But what else is there? Well, we could have a carbon-12, and then we'll throw in one deuterium. And so this is another molecule. Do you see? And so how many is that? Well, we can get up to 4 deuteriums, so that's 4. Except there's some, is there some duplication? Yeah. So that's 1. We could put a deuterium here, deuterium here, deuterium here. Oh, actually, no. We could put, if we move the deuterium, does this constitute a different molecule? Let's say if I put the deuterium on the top, would that be a different molecule, or would that be the same molecule, just rotate it? Different molecule?
Is it gonna because of its structure?
Structurally, they're the same, but would this be a different, or would this be the same? You know, just kind of rotated like the clock handle. And so, different? It's actually, it's not different, it's the same. If we can rotate this 90 degrees like this, then we have the same thing. So if you take the molecule and just rotate it, then it's the same. It's like if you park the car with the front end this way and park it with the front end this way, are they two different cars, or the same car just parked different ways? Same car parked different ways. So this is the same molecule, just taking the snapshot, the photo is just taken at a different time. You know, it's maybe rotating, whatever. So it's actually the same. So as far as this goes, then we're going to have, okay, how many of these? We could put it here, here, here. Well, that's the same thing. But if we put 2 deuteriums on there, now is this different? Well, okay, if I put 2 deuteriums across like this versus 2 deuteriums adjacent to one another, are they the same? Are these the same thing, or are these different? They are different, however, you have to know something more about the structure. This is what we call tetrahedral structure. A tetrahedral structure is, it turns out that you can't tell here. They totally look different, but it turns out they're the same. But this is organic. Actually, this is Chem 1A. So we're not going to talk about this. It's actually the same. So if we count them, how many do we come up with? A bunch. In other words, if we're doing this by the specific molecule, then what we have to do is we have to figure which one we're going to use. Maybe the most common one, which is this. And so usually, if we do it by moles of molecules, do you want to go through and figure out how many molecules there are and then what each one's abundance is? No. We just take the average, right? The average mass. And so this is just too many molecules. I mean, Avogadro's numbers worth of molecules. This is about 25 liters of gas is a mole, roughly. And so if you take 25, there's so many molecules. Innumerable, you can't count them. And so we aren't going to do it. But it's okay. Here. Plus, oxygen is going to yield what? This is what type of reaction? This is a redox reaction, and it's...
Single replacement?
No. Single replacement, we have to have an A plus BX. This is, you're saying this is our A, this is our BX? It looks like a single replacement. You're right, it does look like a single replacement. However, you have to be careful because this turns out to be combustion reaction. And so if we have methane and oxygen, it's not. We're not going to treat that as single replacement. Oxygen is very rarely the A. In fact, never is the A in the A plus BX. If it's a combustion reaction, what does it form?
CO2 and water.
CO2 and water. That's good. Let's balance this. So we have 1 carbon, 4 hydrogens, which means I need how many? Water? 2. And let's count the oxygens. We'll save this oxygen for last because this is alone. If I save this oxygen for last, then changing this will change the number of carbons, which screws everything up. If I save this oxygen for last, that changes the number of hydrogens, which changes the number of methanes, which screws things up. If I change this oxygen, or save this oxygen for last, it doesn't screw anything else up. And so we save that for last. I have 2 plus how many here, oxygens? 2, there's 4. 4 oxygens total, and then I need just 2 O2s. And so I could just do 2 moles of O2, or I could do 2 molecules of O2. But we run into the same issue. With O2, it's a little bit easier because we have O16, O17, and O18. So it's a bit easier to figure out the count because there's only 2 atoms that we have to figure out all combinations for. And we don't have this stuff to deal with. O16 is by far the most common. And then O16, I think O18 is the next. But it doesn't matter. Let's just go down the list. This is not by abundance. And then O16, O18, and then 16, that's all the 16. So we go 17, 17, 17, 18, 18, 18. So 1, 2, 3, 4, 5, 6 different molecules. So it's not crazy. Like methane would be kind of crazy. It'd be a lot of different molecules that we'd have. So if we're doing it by molecule, which one of those 6 or which 2 of the 6 are going to react in this? Probably the most abundant one. The most abundant one would be two of these here. That's if you're working with individual molecules. And then we form 2 moles of CO2, or I mean not 2, 1 mole of CO2, which would be 2 molecules. And then we end up with 2 moles of water, or 2 molecules of water.
How do we get 2 molecules of CO2?
I'm sorry?
How do we get 2 molecules of CO2?
Oh, it's a mistake. My mistake, sorry. All right, if I do it by mole, then we have the molar mass. So we could do, less convenient would be the mass relationship. So let's take a look at the mass relationship. What's the average mass of a methane molecule? And so I could do this one in my head because I know carbon, what is carbon? 1201. And then each hydrogen is 101. So 4 times 101 is 404. So 12 plus 4 is 16. It would be 1604. Do you see? So the 1 mole of methane molecules will weigh 16.04 grams per mole. And since we have 1 mole, it's 16.04 grams. So I'll just leave it at grams. That's how much 1 mole weighs. How about 1 molecule? 1 molecule would be the same, 16.04 U. However, this is tricky because that's the average weight of all these molecules. Do any one of these molecules weigh that? No. None weigh that. So it's like if you take the average of, let's say, a nickel and a dime. What's the average of a nickel and a dime? 7.5 cents. Is there a 7.5 cent coin? No, there's no such thing. So this is the average mass, but there's no molecule that weighs the average amount found in nature. All these will have their individual masses, and then we just average those based on their abundance. Oxygen 16.00, so 16.00 times 2 gives us 32.00 grams of oxygen.
Is it 4?
Oh yeah, you're right, times 2. Times 2 would be 60 64. So I'll just do 2 times 32.00 grams, which is 64.00 grams. And 2 molecules of this would be 64.00 U. That would be the average. Carbon's 1201 plus 32 from the 2 oxygens is going to give us 44.01 grams. 44.01 U. Water. Oxygen 1600 plus 2.02 from the hydrogens. That gives us 18.02 grams. And the 2 molecules would weigh on average 18.02 U. So this asterisk is the average mass of all isotopes, of all isotopes. So this one we derive pretty easily, correct?
Yes.
Would you be able to derive this one just as easily? No, to derive the mass relationship, the mass relationship is like this. 16.04 versus 64. You know, so the way we do this is you have 2 choices, and we do it one way usually. And this is the way we do it here. So we have what we call the conversion factors. And so the mole to mole. The mole to mole is like 95% or maybe even higher, 98% of problems. We use mole to mole. And then we have a gram to gram. Maybe 2% of problems will do gram to gram. This is direct conversion. So for mole-to-mole conversion, we get the mole ratios. These are the mole ratios here. So if I have 1 mole of methane, how many moles of oxygen do I need? Here. 2 moles. And so I come up with this mole ratio. This mole ratio converts moles of oxygen to moles of methane. So it's a moles of oxygen to moles of methane conversion is what we use that in dimensional analysis. Or I could do 2 moles of oxygen on the top and 1 mole of methane on the bottom. This converts from moles of methane to moles of oxygen here, conversion. And what we do is we take ratios. So I can continue. 1 mole of methane is going to produce how many moles of CO2? That's going to produce 1 mole of CO2. So this converts from what to what? This will convert, this is moles of CO2 on the bottom. This converts from moles of CO2 to moles of methane. Or I invert it. 1 mole of CO2 requires 1 mole of methane. Here. Let me know if it's not legible. It's just moles of CO2 over moles of methane, 1 to 1, etc. So we could do this for everything in there. which we can do. The gram-to-gram direct conversion would be like this. Rather than saying 1 mole of methane, I would say 16.04 grams of methane requires how many grams of O2? 64.00 grams of O2. So in terms of ease, the mole-to-mole conversions are easy. The gram-to-gram conversions aren't terribly difficult, but they're less convenient. And so we can invert this, 64.00 grams of O2 for every 16.04 grams of methane. Sometimes we'll do this. Sometimes we will use these, but not often. Instead, what we're going to do is we're going to do an extra step. So if I want to do a mass-to-mass conversion, I don't usually do it direct, unless I'm given the ratio. So let's say this might seem like a lot of work, but this actually turned out to be a lot less thinking, a lot less work, because this is what we call the heart of the stoichiometry map. At the core of stoichiometry, we have a mole-to-mole conversion. And so what we do is we convert from moles of A to moles of B using a mole ratio. So we need to know, how many moles of A, how many moles of B are present in the reaction as given or in the formula. And there are other mole-to-mole conversions that we can do. I should have just added that here. Mole ratio comes from two sources. One is this, the balanced equation, or two, the formula. An example of the formula would be, let's say H2O. How many moles of hydrogen and how many moles of oxygen do I have in a mole of H2O? So if I had 1 mole of H2O, how many moles of hydrogen do I have? 2. Yeah, I have 2 moles of H atoms. There aren't hydrogen molecules in H2O. There's no hydrogen molecules, there's no oxygen. There are hydrogen atoms, which is different. The hydrogen in here are atoms that are attached to the oxygen, like this, versus H2, gas, are 2 hydrogens that are linked together like this. And so it's not H2 gas. And so a lot of people will write 1 mole of H2O contains 1 mole of H2. It doesn't contain 1 mole of H2 because that's hydrogen gas. And each glass of water you drink doesn't contain a mole of hydrogen gas, does it? If it did, then we could power electric vehicles like the Toyota Mirai using hydrogen to generate the electricity. Anyway, the H atoms, or we could say that the 2 moles of H atoms for every 1 mole of H2O, or we could say that there's 1 mole of O oxygen atoms in every 1 mole of H2O, etc. These are just things that we get from the balanced equation of the formula. We can come up with these mole ratios, which are very convenient to use. Unplug this. So if I want to do a mass-to-mass conversion, I don't usually use the mass ratio. 98% of the time I won't use the mass ratio. So let's look at mass to mass relationships. And so I'm always going to fall back on this mole to mole conversion here. And so the mass to mass ratio, or relationship here, maybe about 2% of the time, I'll do direct. You know, so for example, if I'm given the mass ratio, then I'll use it. But I'm not going to calculate it. If given the mass ratio, and so, for example, if you're given this, water contains 11% hydrogen by mass, then I'm going to use it, you know. So if I had 100 grams of water, then I know there's 11%, so that's 11 grams of hydrogen for every 100 grams of water. Then I'm going to use it, and so this is going to give me 11 grams of hydrogen are contained in there. You know, I don't have to go, I picked too easy of a number because I didn't want to calculate anything. Just 100 grams. If I had 200 grams, how many grams of hydrogen? 22 grams, you know. If I had 150 grams, then I'd have half of that, 16 and a half.
Other than H2 or just H?
Just H. Yeah, I made a mistake here. It's not H2, it's just H, atoms. Not H2. We have to be very careful with that, you know, because in this case, when we're doing this type of stuff, when we're looking at inside the formula, it's not molecules within molecules. I don't have molecules within molecules. I have a single molecule with all the atoms attached to it. So I need to be careful of that. This is a very common mistake I see all the time. It's people, yeah, and we know hydrogen's H2, but we don't have H2 molecules and H2O molecules. Molecules within molecules. Or another example might be like this. You know, another example was there is 2.02 grams of H in 18.02 grams of H2O. And so I could do the same thing. Well, I'll go 100 grams of H2O, right? And then I'll use this mass ratio. They're giving me the mass ratio here, 2.02 grams of H for every 18.02 grams of H2O. And then I'll calculate it. You know, and when I calculate it, it'll give me the same answer, 11 grams of H. You know, and so you're given the mass ratio in two ways. One, it's the percent, and we say clearly this is percent by mass. Or two, you're just given the grams of each component and the total grams. And so we can come up with it this way. So on occasion we'll run into this kind of problem where the quickest way of solving it is just to use what's given. And since they give it to us, we don't have to deal with it. However, 98% of the problems we don't. 98% of the problems you might think is more work, but it's actually less work overall. And this is the issue. You know, when you do And I know a lot of people, you know, based on the quizzes, a lot of people want to just use algebra, and they'll use some new algebraic equation for every problem that they encounter. And they'll start dividing this and multiplying these numbers and doing all kinds of stuff. But you don't want to do that. You want to have one way of doing it and doing it the same way each time. That way it's easier to remember, and also you can solve more complex problems. So what we need to do, what that one way of doing it is, and I know people have been avoiding using this method for their own. I mean, you're not wrong to do it algebraically, but what's going to happen is you're going to hit a ceiling where the problems are going to get kind of more difficult, and it's going to be very difficult to solve the problem the way you're doing it. And so 98% of the problems, we're going to use the core, you know, the mole-to-mole conversion, and then build up from there. And so here, moles of A to moles of B. This will be the core of it, of the stoichiometry. And we always revert to this in particular problems. And so if we're given the grams of A, we go from the grams of A to the moles of A. And then from the moles of A, we go to the moles of B. And from the moles of B, we can get to the grams of B. And the way we do this is the gram to mole conversion and the mole to gram conversion, we use the molar mass. So these, we need the molar mass. Of A and B. So if I have say I have 100 grams of water, and I want to figure out how many grams of H2O I have, then I would do it like this. I would start off at 100 grams of H2O, and then what I want to do is I want to convert that to moles of H2O. And so I need to get rid of the grams of H2O and replace it. And so this is just the molar mass flipped over. And so it turns out that how much does a mole of H2O weigh? Well, 2 moles of hydrogen weighs 2.02, a mole of oxygen weighs 16.00. So the molar mass is 18.02. Here. And then I can cancel out. You have to show me the units. That way, sometimes what you can do is you can get the correct answer, but in the wrong way. It just so happened that you got lucky and it worked, but it wouldn't work if the numbers had changed. And then what we're going to do is we're going to do a mole-to-mole conversion. For every mole of water, there's how many moles of hydrogen? Just from the formula, there's 2 moles of hydrogen atoms. And then how much does a hydrogen atom weigh? A hydrogen atom weighs, actually, if we're just doing this, we could either go with 3 sig figs or 4 sig figs. Hydrogen to 3 sig figs is 101. What is it to 4 sig figs?
1.008.
Yeah, 1.008. In this particular problem, it's better to use 1.008 rather than 1.01 because it won't limit the number of sig figs. So 1.08 grams of H atoms per mole of H atoms. And so it depends on how many sig figs we had here. If we had 3 sig figs, like 100 dot, then we'd get 3 sig figs in our answer. Or 2 sig figs or whatever it comes out to. Let's see how many. grams come out of this particular problem. So 100 divided by 18.02 times 2 times 1.008. .1875 ... grams of H. To 3 sig figs, this would be 11.2 grams of H. We call that 3 sig figs there. To 4 sig figs, 11.19 grams of H, depending on how many sig figs we need to report. Most of the problems we are dealing with are 3 sig figs, most of them. So that might seem like more steps, you know, than something like that, you know, but the usefulness of this is we can solve much more complex problems, because what we're doing is we're building a map. Let's say you move to a new city and you're trying to figure out where things are. And so you want like a little core place that you know, you can always, if you go here, you know where you're at, right? But then you start branching out. When you start branching out, you start branching out and you get further and further away from the core. It's always nice to be able to go back to the core place, right? And then you know where you're at. But the situation is if you don't have any core place, then you branch out in the city and you have no idea where you're at, right? This is like algebra. You're doing a new algebraic equation for every single problem. You're going to have trouble because you're going to be out there, someplace that's unknown, and you don't know how to get back home, kind of thing. And so this way we always know, because all the hard problems are they're just additional we're just branching out a little bit farther, one step farther, one step farther, one step farther out. But my target is always getting back here so that I can figure it out in the end. And so if you look at all the challenge advanced problems, that's all they are. They're maybe 2 steps out or 3 steps out. It's not difficult. You just got to find a path back to the core, and then you can go from there.
That gold one.
Like the gold one or whatever. That's just a few steps out. That gold problem, a few steps out. We'll do one that's not terribly far out. That should be fairly. One of the reasons they want to ban methane, do you know one of the reasons they want to ban methane? Even from cows, they want to try to get the emission from cows reduced, because methane is produced in cows. Not ozone. Ozone's a different problem. Ozone is the UV layer, and the ozone, what's killing off the ozone are the CFCs. The chlorofluorocarbons. The chlorofluorocarbons are still used in a lot of countries, and so the U.S. is not an issue. The U.S. has banned them for decades. The problem is many other countries continue to use it, and you can't, even if we ban it in here, it's already done. It's like a lot of the pollution in the Pacific doesn't originate from the U.S. So like the straw ban and all that stuff, the U.S. doesn't dump a bunch of plastic in the ocean. The other countries do. And so we've got to work on foreign relations for that. But, I was in Hawaii doing it. Have you, the beaches in Hawaii, have you been there recently? So much plastic. It's amazing. The amount of plastic. It's like a percentage. It's not like part per thousand or part per million. It's percentage. You go to the beach in Hawaii, you look at the sand, there's a bunch of plastic fragments from waste that came from Asia all over And so there's volunteer opportunities, so I volunteered for an hour or two cleaning up the plastic waste there. But, yeah, so anyway, so the reason is, and the thing is, probably, I don't think we can really ban methane combustion. I think probably the thing is that some chemists and engineers have to get together to figure out economical ways of capturing the CO2 if they're worried about the CO2 waste. CO2, even though CO2 is completely spent for combustion, people want to use it. You know, what can you do with CO2? You know, it's already burnt. You can't really use it as fuel. But what people are trying to do is they're trying to reverse that, you know, and make, from CO2, they're trying to make methanol. And they aren't making the methanol to burn, they're making the methanol to do other things with it. Although you can burn methanol as well.
Well, you get like methane.
Yeah, you get, well, when you burn methanol, you get CO2 again. You know, but they're trying to use methanol to make other chemicals. The problem is that, I mean, it can be done. It's just expensive to do. And so let's do this example. If we burn 1 pound of methane, how many pounds of CO2 will that generate? So if we had a mass to mass ratio, it would be easy. We could do this in one step. Which I guess, do you want to memorize how many pounds of CO2 for every pound of methane? You want to memorize that? No, and so what we do is we try to go about this a little bit differently. We go back to the core, our stoichiometry, and in our core stoichiometry, we need the molar masses. Do you want to calculate the molar masses? You know, we have it memorized in grams. Do you want to memorize it in pounds or ounces? Do you want to do that? No, we don't want a different equation for every single problem we solve. What we want to do is we want to use the same core equation for everything, if possible. And so automatically, if I'm thinking I have pounds here, the first thing I want to do is convert it to grams, because I know the molar masses, I've memorized them for grams, and I don't want to memorize a bunch more in ounces, pounds, or whatever. And so the thing I'm going to do is this. So let's go with exactly. In exactly 1 pound of methane. So what I'll do is I'll just start off with 1 pound of methane, and then I need to convert that to what? Grams. Does somebody remember the conversion factor from pounds to grams?
It's like 453.6.
Yeah, 453.6 grams per pound. As long as you use this once in a while, it's easier to remember. If you haven't used it in a while, then it's hard to remember. But you don't have to remember it. If you forget it, it's not a problem. This is one you don't have to memorize. Maybe it should be. I don't know. All right, now we have grams of methane. Okay, so where should we go from grams of methane?
1 mole of methane
Yes.
is equal to how many moles of CO2?
1 mole, no, we can't do that here because we got to get rid of what? We got to get rid of grams of methane. And so on the bottom here, we need grams of methane. Otherwise, it's not going to cancel. This is the dimensional analysis. We need to cancel out the grams, which we have here, and we need to cancel out the methane. So we have,
Grams to grams.
so it's going to be gram to mole conversion using what?
Molar mass.
Yeah, the molar mass. How much does a mole of methane weigh in grams?
It's like
16.05, sorry, I miscalculated it. Hydrogen is 404, carbon's 1201. And so 12 and 4 is 16, and then 04 plus 01 is 05. Okay, then where do we go?
The moles of CH4.
Yeah, then we do a mole to mole conversion here. Mole to mole conversion is going to be
1 mole of CO2.
Yeah, 1 mole of CO2
to 1 mole of methane.
to 1 mole of methane. Good.
And the grams.
And then to grams. So 1 mole of CO2 weighs how many grams?
44.01.
Okay, so first we make sure everything cancels. So moles of methane cancel, moles of CO2 cancels, and that leaves us with grams of CO2. But I don't want grams of CO2. I want,
Oh, you may multiply it by
Oh, and then you
453.6 grams
yeah. On the bottom I need 453.6 grams.
was 1 pound
Or,
of CO2.
yeah, 1 pound. And this one's good for anything. It doesn't have to be CO2.
Okay.
And so the grams cancel, leaving us with pounds. Also, the 453.6 cancels on both sides here. We don't have to worry about that. So let's go ahead and calculate it, what it comes out to. Um, 4401 looks like divided by 1605. Did I get that right? What did you guys get?
2.742.
2.7. Now, how many sig figs are we allowed here?
4.
4. So 2.742. And then I'll carry an extra one because I'd like to show the rounding step. So this is the concern. For every pound of methane you burn, you get 2 3/4 pound of CO2. Hey, doesn't that violate the law of conservation of mass? Does this violate the law of conservation of mass? No, it doesn't, because what we have here is you have to look at the entire equation. You have to look at the total mass of methane and O2 and compare that with the total mass of CO2 and water. And so let's do this problem again, except in this case we're going to calculate how many pounds of O2 do we consume. So in the next example we're going to do, if we burn 1 pound of methane, exactly, how many pounds of O2 will be consumed? So can you set it up?
Be consumed.
How many pounds of O2 are consumed? Consume means it's on the left side of the reaction. On the left side of the reaction, because the reaction, probably should rewrite it up here. The reaction is methane plus 2O2 yields CO2 plus 2H2O. And so when methane reacts, it reacts with O2. Both of those are consumed. When they're consumed, we form these as products. Both of these are formed, CO2 and water. So if I start off with 10 pounds of methane and O2, I'm going to end up with 10 pounds of CO2 and water. But the ratios are going to be different, though, the ratio of each reactant. And so let's calculate how many pounds of O2 are required to burn that. When there's no solutions manual available, we usually check with other people to verify the answer. Somebody else? Yeah. Yeah, so it's pretty much the same stuff. I know it seems like we should be able to shortcut this, but I never shortcut this. I just do it the long way each time. And so I would start off with 1 pound of methane and then convert that to moles of methane. Oh, no, I can't go to moles. I'd start off with 1 pound of methane and convert it to grams of methane. And then convert that to moles of methane. Sure, that's on. And then I'd convert this to moles of CO2. And then I would convert it to grams of CO2. And then I would convert it to pounds of CO2. So you have to think of it like this, like if you go to different parts of an unknown city, you might think there's a more direct way. There's got to be a more direct way, but what you end up doing is you always end up taking the long route. You go back to your home and then go, you know, that kind of thing. And so you might think, this is kind of long. But anyway, what did you get again? 2.2? 2.245. Give me one more digit because I like to see the rounded digit. 4? Okay. Pounds of oxygen. And then when we burned 1 pound of methane, how many pounds of water were formed?
So, quick question.
Uh-huh.
How was the first problem different to that problem?
The difference is the mole-to-mole conversion here. We went from moles of methane to moles of CO2 here. In this one, we're going from, oops, this is wrong. I'm doing the same problem.
It would be 32 then, right?
Yeah, it'd be 32, all right. This should be moles of methane to moles of O2. And this is 32.00 grams of O2 per 1 mole of O2. Yeah, thanks. Now it's different. Also, you have to watch out, too. Because if you do the same path over and over again, sometimes you repeat the same mistake.
So in the end, it would just be 32 divided by 16.05.
Yeah, right.
And that
Yeah.
doesn't give us that.
Right.
They give you at 1.99.
It gives you 1.99? You're getting 1.99?
Would you guys do differently than that?
Well, I had did the same thing and then everything canceled out, but like the random versions are just based by 36.04 except by 6.05.
36?
Yeah, I mean, oh wait, for mole of O2. Oh, well, it is the same thing and then it should cancel, so it's basically just 64.00 divided by 16.05.
Oh yeah, because
Check it again.
it's supposed to be
Isn't it supposed to be 2 moles of O2?
2 moles of O2. Oh, yes. Right.
Oh, yeah.
This is the problem here. This is, rather not, that should be double. 2 moles of O2 per 1 mole of CH4.
3.988.
What do you get?
3.988.
3.988. All right. So let's fix this. 3.988 8. Give me one more digit. It's actually 3.9875
Yeah.
pounds, which will round to 3.988 pounds. We'd like to see the drop digit to see how it was rounded.
If we don't do the drop digit, we can mark that wrong.
I don't mark it wrong, but I need to see it though. The situation is this. Sometimes what we do is we take this number and then do additional calculations with this particular number. If we do that, we don't want to use the rounded number. We'd like to use this one for additional calculations. That way we can minimize rounding error. Let's say it came out to 3, because this is midway between 7 and 8. You know, it's 5. So when we have a 5, do we round down or round up if it's midway? We round up, but either way, it's a more significant rounding than the other. How many pounds of H2O was that?
2.245.
What was the first number again? 2.245 pounds of H2O. So one quick way we can check is the total mass that we start with has to be the same as the total mass we end up with. So we had 1 pound of methane plus 2.74 pounds of O2 gives us 3.74 pounds of reactant. So we have 3.74 pounds of reactant here. And how many pounds of product do we have? Oh, wait, I'm not doing it right, sorry. This is 1 pound of methane plus how many pounds of O2?
3.988.
3.988, so that's going to give us 4.988 pounds of methane and O2, and that gives us how many pounds of CO2 and water? 274 plus 2.2, so this is going to be 3.999, or 4.999, or 4.999, 4.989.
Yeah, that's close enough.
Yeah, is that close enough?
Yeah.
They don't match exactly, but they're close enough because of what? Why are they off?
The rounding.
Rounding, exactly. They're off because of rounding. Now, if they were more significantly off, let's say I had 4.988 and over here I had 4.75, then there's something else that's more seriously wrong. No, that's not due to rounding. A more significant difference like that is probably due to a calculation error. So most likely some kind of calculation error crept in there. So what we want to do is we want to familiarize ourselves with this, and then we can do some more advanced problems.
Is this kind of similar to like chapter 7?
Yeah, right. And so what we're going to do is we're going to add branches to this. The additional branches could come in different places. So for example, let's say I want to know how many, rather than how many pounds of CO2, how many molecules of CO2 did I just create? Yeah. If I want to figure out how many molecules of CO2 I created, then I would branch out here. From here, and then I just go to number B. The number B, what I'd use for this branch here is I'd use N sub A, which is Avogadro's number. So for example, if I formed a mole of CO2, that means I have 6.022 times 10 to the 23rd CO2 molecules. Correct? And so, for example, 1 pound of methane produces what number of CO2 molecules? And so the calculation I'd set up is I just start over here, 1 pound of methane, and then I would go to grams of methane per pound, and then I'd go to moles of methane. And then I would go to moles of CO2. And then I would throw in Avogadro's number because it doesn't matter what the mole is. It's going to be what the identity of the compound is, or whatever we're looking at, atoms. It's always going to be 6.022 times 10 to the 23rd per mole. And so this would be 6.022 times 10 to the 23rd CO2 molecules per mole of CO2 molecules. So how many CO2 molecules did we just produce by burning a pound of methane? And so we'll go with...
You don't go back to grams?
I don't go back to grams here because there's a more direct way to go. The relationship is between moles and number, but I don't know. We can if I knew the relationship between grams and number. But I don't want too many paths to memorize. You know, the more things you have to memorize, the more memory that takes up. And the more memory that takes up, the more difficult it is to remember all that stuff. So I get 1.7019 times 10 to the 25th molecules. All right, to the proper number of sig figs, this would be 1.702 times 10 to the 25th molecules. So a little over a mole, like. Is that right? Did you guys get this?
Yeah.
Okay. You know, we can have alternate branches like this. We could have other branches as well, you know. So we could go to, for example, you know, we could add the branch here, let's say, or wherever. Let's do another example.
If you do the reverse, you like the number of CO2 molecules
Yeah.
in 1 pound of CH4.
Right.
Then you do the reverse.
You could do the reverse, exactly. You can go either way. It's like, you know, when you're walking, you can walk to home or away from home or whatever, you know, as long as you know the path. All we're doing is we're making a map. This is a problem-solving map. And the more streets we know in the problem-solving map, the more ways we can get there. So if you're, let's say you're a taxi driver, you know, I guess in the UK or something, the taxi drivers, or in London, they have to memorize every street. Did you know that or something? Have you heard
It
that?
used to be the same thing here, but added the GPS and stuff.
Okay. Yeah, well, now we have GPS, so it doesn't really matter. So you know, if you're driving in a taxi, you don't want the taxi driver to drive home each time, right? You want them to figure it out. But anyway, the more roads we know in our stoichiometry, or the more paths we know in the stoichiometry map, the easier it is to solve more complex problems. All right, so here, If I burn 1 pound of methane, how many pounds of air will that require? Because do you separate the oxygen in air? When you use the Bunsen burner, do you separate the oxygen yourself and then, no, you just put air in there. So how many pounds of air? Not all the air is going to be used. You know, the nitrogen isn't going to be used in air. So we need some additional information here. The additional information we need is this. We need the percent by mass of air, or the percent by mole of air. And so we have to be careful because I told you that air contains how many? Yeah, the two primary ones are nitrogen and oxygen. And do you know about how much oxygen is in air?
20%. I know there's like 78% nitrogen.
Yeah, 78% nitrogen.
And 22% oxygen.
Yeah, we'll just say that. Is that by mole or molecule? Or is that by grams or mass?
I would just.
Air is about 78% nitrogen. Is that N or is that N2? That's good. It's N2. And about 22% O2.
Well, there's a nice trick to memorize the elements or the atoms that they're always in pairs.
Diatomics. There's 7 of them.
It was have no fear of ice cold beer. And,
Have no fear of ice cold
the
blur.
acronym is what it is.
Oh, that's good.
So I saw it one time ago because it's memorized.
Yeah, that's a good one.
It helps.
Yeah. This one turns out to be by mole, not by mass. Yeah. So we have a choice. We can either find the one by mass or we can go ahead and try to calculate it.
Find the percent of each for the thing. 80% of
Yeah.
mass of hydrogen.
That we could do that. We could do that. Well, let's do that way. That sounds like a good way of doing it.
Finding the mass.
Yeah.
It's not that bad.
This is by mole, or we can figure out the mass percentage. Can calculate the mass percentage, mass percent composition of a mixture. The mass percent composition of the mixture is the percent of nitrogen by mass is equal to the grams of nitrogen over the total grams. The total grams is the grams of air, so this is going to be grams of nitrogen times 100%. Grams of nitrogen over grams of air times 100%. And we could figure out the percent oxygen. Percent oxygen is going to be the same thing. It's going to be grams of oxygen over total, or air, grams of air times 100%. So let's figure out the percent oxygen here. Yeah, so it depends. Okay, here, this is percent by mole. And so it's going to be a little bit more complicated. Because do we have 1 mole? 1 mole of oxygen is 32, you're right. But
So not like the mass of air like 60. Don't you need like to add them together? Get the total air.
yeah. So what we can do is just do this. We can assume 100 grams of air, or no, 100 moles of air. Let's assume 100 moles of air. If we have 100 moles of air, how many moles of O2 do we have? 22 moles of O2. And then 22 moles of O2 weighs how much? Well, we can figure it out by taking 32.00 grams of O2 per 1 mole of O2. And that's going to give us how many grams of O2? So 22 times 32 is 704 grams of O2. Now, what we need to do is we need to figure out, well, this is for, we're going to calculate the percent O2. This is grams of O2, sorry. Now we've got to figure out how many grams of air. So we have 704 grams of O2 plus how many grams of N2 do we have? And so it's going to be how many moles? 78 moles of N2. Now nitrogen's 1401, and we have 2 of those. And so this is going to be 28.02 grams of N2 per mole of N2. So that just double it. 1401 doubles to 2802. And so that's 78 times 28.02. Yeah. What did you get? I got 2,185.56.
Oh yeah.
2,185.56 grams of N2.
704.
So the total is going to be plus 704. This is going to give us a total of 2,889.56 grams of air. Now, I'm not allowed this many sig figs, but I'm just going to carry it because I have to do additional calculations with this. And so the percent O2 by mass
It's like 24.
is the grams of O2, 704. This is actually probably 704.0, is that right? 22 times 32. I forgot to do my usual carry extras. Actually, we're not even allowed that. This is only 2 sig figs. So 704, we'll just leave it at that. Divided by 2889.56 times 100%. So 704 divided by 2889.56 times 100 is 24.36% O2 by mass. So by molecules, if I have 100 molecules, 22 of the molecules will be O2. But the O2 is heavier than N2. O2 weighs 32, N2 weighs 28. And so the percent by mass is a little bit bigger. Do you see? Air is 24% oxygen by mass, 22% oxygen by molecule or moles. And so the numbers are different. So in this case, what I'll probably do is I'll just do a mass ratio for this. I could have looked this up instead. In fact, if I were, I don't know, you know, the more complex problems is, yeah, you probably could figure this out, but oftentimes, like in the stoichiometry problem, we don't want to have too many branches leading into it, so don't want to lose too many, because too many students will get lost, so I'll probably just give you something like that. All right, so if I have 1 pound of methane, then it's the same thing here. I'm going to go to grams, and then moles. And then moles of O2. To grams of O2. In this case, I'm going to go to grams of O2, 32.00 grams of O2 per 1 mole of O2. Sometimes people will do this. They want to cancel out the 2 moles of O2, and so they'll use 64, but I don't do that. You get the same answer. But I always use this one because it's easier to remember. And then we go to grams of air, and we just calculated it. That is that for every 100 grams of air, now we're only allowed 2 sig figs here, so I'm just going to go to 24 grams of O2. I could carry extra to avoid round-off error, and so sometimes I'll do that, doing 24.36, but those percentages are off anyway, so I'm just going to go 24 grams of O2 here. So let's go ahead and do this calculation here. It's going to be 1 pound, so 453.6 divided by 16.05 times 2. Times 32 times 100 divided by 24. And I need, oh, actually this is grams, sorry. I need pounds of air, so I need one more here. I need to convert it to pounds, 453.6 grams. So I need to divide by 453.6. And I'll need 16.61 pounds. Now, as far as sig figs go, I only have 2 sig figs, so I'm going to convert this to 17 pounds of air required. Is that what you got?
I got 18.
18?
8.18.
8.18. All right, let me double check my calculation here.
I got 16.612.
Double check my calc. First on, I want to double check is the dimensions cancel. Pounds, grams of methane, moles of methane, moles of O2, grams of O2, grams of air. Both, no, air stays, grams cancel. Grams cancel the grams, that gives me pounds of air. So the 453.6 cancels, and so it's
64 divided by, or times 64 times 200
yeah.
divided by 1605 divided by 24. I got the same thing.
You got the same thing?
Yeah.
All right, Jason, maybe you can check yours again. Other people get the same?
What are you doing?
Yeah, I get the same thing.
Is it supposed to be 2 moles of O2 on the bottom for the, under the grams?
You could either do 1 mole or 2 moles or 1 mole of methane, or you could do 1 mole or 2 moles of H4 and then 64.
Well, this I leave 2. This could be 2 or it could be 10, you know, or whatever. The ratio stays the same. If the ratio stays the same, it's not going to change anything. All right, this made the calculation more complicated, and so this is more complicated. This one we could look up. And so I probably lost a lot of people with this calculation here. And so if I gave you the percent by mass, could you do it? Yeah.
So there's
Look.
this is pounds of air with
Air contains both nitrogen and oxygen. Nitrogen's not going to react. It's only the oxygen in air that reacts. Nitrogen will just be a spectator.
Okay, so we didn't put nitrogen inside the.
No, we don't include nitrogen. It's all included in air here. Not all the air is consumed.
Only because CH4 reaction with O2
Yeah.
or nitrogen spectator, like you said.
Right.